네, 한성민 씨 안녕하세요. 네, 박건우 씨 안녕하세요. 자, 여러분, 지금 아직 정상목 씨 안 오신 것 같은데, 시작하도록 하고요. 질문 있으면 먼저 질문을 해주시고, 예, 해주시고, 그 다음에 시작을 하도록 하겠습니다. 네, 정상목 씨 안녕하세요. Okay, so if you don't have any question on previous lecture, let me just directly move to the content of lecture 19. So this is the first discussion about our green function. Okay, so think about a quite a simple equation like this. So yes. So you know now, you know the name of this equation. This equation is called the Laplace equation. So, and when we consider the Laplace equation in one-dimensional space, you can solve it quite well. So yes, its discretization is quite simple, and you can also make a matrix for it. So now you have phi matrix, and here you have a certain matrix corresponding to the second order derivative, and here on the right hand side you have usually all zero, because the right hand side of your Laplace equation is zero by definition. But there is one thing we have to keep in mind, that in order to make a certain equation, differential equation, is accessible to us, so means that if we wanted to have some determined solutions for certain differential equation, we have to specify also boundary condition. So your discretized system shown here should contain both of equation itself and corresponding boundary condition. Usually, in this simple 1D case, the leftmost point and the rightmost point are regarded as what? Regarded as the boundary node. So here we have the first row and the last row corresponding to the boundary condition. So although in usual case the right hand side term vector contains all zero component, however, for example, here and there, the first and the last entries of our right hand side vector, so we have phi at x naught, for example, if we start from our one-based index system, then we will say this way, and also we will have phi at x sub n, the last node. Okay, so when you have a look at this matrix equation ax equal to b, so you can easily understand it both contains the boundary condition and the equation of our interest. So that was your first knowledge on the computational microelectronics. So after that, we have discussed many different equations, typically the Poisson equation, and also you have learned about how can you discretize another equations called continuity equation. That was your previous study. And from now on, I wanted to proceed with a different type of methodology, so solution methodology. So this was the Laplace equation, but this is not the only information we can achieve from this Laplace equation. Let me just consider another one. So here now we have still the second order differential equation. Yes, and previously the right hand side of your Laplace equation, by definition it was 0. However, instead of that, now we wanted to introduce certain source term. Yes, so you can immediately understand this is no longer the Laplace equation. In order to say something is the Laplace equation, you know that the right hand side, the source term, should vanish. However, now I'm saying that instead of that, I will just say certain non-zero right hand side, the source term. So we will try to say this is the newly introduced source term. So it is not the Laplace equation any longer. Okay, anyway, we have already used or solved the Poisson equation, so it can be regarded as a Poisson equation. Yes, certainly we have a non-zero, non-vanishing right hand side source term, so it simply means that this is just a kind of the Poisson equation. Yes, its calculation is not that difficult. Also, of course, we have to specify boundary conditions. So, of course, we can think about many different uh, mm, possibility. However, why don't we just introduce homogeneous Dirichlet boundary condition? So, simply speaking, I'm saying that so x equal to 0. So, this is nothing but x1 that is vanishing. Also, the last one, the length L, and corresponding to the last node x sub n, also vanishing. Okay. So, are you with me about this new new equation? Certainly, we cannot say this is Laplace equation. No, it's not Laplace equation. However, so if I have no previous knowledge about the Laplace equation, I would like say this is a kind of the Poisson equation where the source term is really highly concentrated at x sub naught. Yes. But anyway, since we have made a certain discussion about Laplace equation, then maybe we can try to make a certain, I can say, certain relationship between our Laplace equation and a new equation. Here we have the original equation and the equation introduced later, and the relation between these two equations is quite simple. Yes, so we have now just added one single highly concentrated source term and measure the response of our solution variable phi. Okay, so although I have not discussed about the physical meaning of this procedure, I just ask you whether you can understand the newly introduced equation, and of course you can think that this can be solvable. So do you have any question about this newly introduced equation and its boundary condition? So if you have any question, then please let me know. Okay, good. X naught, okay. X naught is a given constant. A given number, given position. So, simply speaking, that is a really good question. Thank you. And think about this one. So, let's say this is your x-axis, and yes, say this is corresponding to 0, and this is corresponding to L. Yes, so usually what you do in Laplace equation was like this. For example, I just say that at the leftmost node we have 0. Anyway, and the and at the rightmost node we have non-zero value, for example 1, and with this boundary condition we can solve the Laplace equation, and as we all know, the solution is just a straight line linear function, because linear function always vanish when we have the second derivative. But point is, now let's try to interpret the form of this lower equation, so newly developed or newly introduced Poisson equation. In this case, I'm saying that the boundary value is just vanishing at both boundary nodes, and x naught is a given number within the range of 0 to L. So say that, for example, this is x naught. X naught. This is given by certain way. Then you know that now, although any other place we have no source, however, at x equal to 0, we have highly concentrated source. Yes, that is our case. So simply speaking, if we treat this Laplace equation just like a certain how can I say, equation for describing our electrostatic potential, then previous Laplace equation just says that the left plate was biased to 0 and right plate was biased to 1 volt. Then what will be the potential distribution between them? That was the physical meaning of this Laplace equation. But now, when we go to this lower equation or newly introduced equation, Now it says that the left plate and right plate, both of them are biased to the ground. However, in the parallel plate capacitor at a certain position called as x naught, there exists a sheet charge. Then what will be the potential distribution of this inside this parallel plate capacitor? That can be obtained from the solution of this Laplace equation. Okay, so Mr. Han, so therefore, if I answer your question simply, then I would say that x naught is just a parameter given by the problem itself. However, from the viewpoint of physical sense, that is just representing the location of the source term inside our system. So, Mr. Han, is it enough for your question? Or if not, then please ask me further. And also, for other students, if you have any related questions, then please let me know. Then I can answer your question. So, so I just explained what is the physical meaning of this new equation. Now, this can be regarded as another potential distribution when we have internal perturbation. Okay, so simply speaking, the solution of the Laplace equation and solution of this Poisson equation will have much different information. So why they are different? So in the case of a Laplace equation, we just observe the response of our solution variable with respect to the terminal excitation. We can apply one volt to right contact, or we can apply one volt to left contact. That information can be obtained from the Laplace equation. But in this Poisson equation, instead of that, we just obtain the potential distribution when the charge is injected or charge is existing at a certain position. That is a simple difference between Laplace equation and Poisson equation, and you can easily understand they should be quite different. Okay, so in this simple introduction to the green function, so I want to just say that let's first try to solve this system quite similarly with the Laplace equation. Simply means that I will assume we have made x1, x2, and blah blah blah, and up to x sub n. Obviously, this is corresponding to 0, and this is corresponding to L, and any x sub I can be obtained by I minus 1 times L divided by n minus 1. And you know it much better than me, so we can assume this kind of uniform spacing for our one-dimensional space. Then let me just try to solve it. But before solving it in a numerical sense, since this system is so simple, so I just have a try to solve it analytically. Say this way. Okay, so are you all with me? So this is the solution procedure, analytic solution procedure. Okay, maybe something will happen at x naught. Yes, since we have introduced something strange at x equal to x naught. However, except for x naught, we will have just normal Laplace equation. So why don't we just divide our domain into two pieces, so region 1 and region 2. So simply speaking, when x is smaller than x naught, this is corresponding to region 1, certainly we have the x smaller than x naught. So we have introduced Dirac delta function. So you know that this is the Dirac delta function. So before continuing our discussion, I should ask you whether you understand the Dirac delta function or not. Please respond to my question, all of you. You know the Dirac delta function. And how about Mr. Jung and Mr. Park? Yes. Okay, great. So Dirac delta function, when integrated over x-axis, including x naught point, we will have just number 1. And when integrated over a certain range which does not contain x naught, it will immediately give us just 0. So think about this one. In this case, Dirac delta function certainly vanishes. So we can certainly say, this will be the equation for a certain range which whose x value is smaller than x naught. Quite similarly, we can also say that when x is larger than x naught, then of course we can also have this function or this equation. Yes, so from these two equations, now you can solve it individually. So from this one, now you understand anyhow your phi should be certain form of ax plus b. And also this guy says phi should be cx d. And you know that that should be a continuous function. So we have to have a continuity at x equal to x naught. Then how can we set the coefficient a and b and c and d? So let's just say phi at 0 should be 0. This is the boundary condition. And when we just insert this x equal 0 to ax equal to b, then we can find this b equal to g condition, or b equal to 0 condition. So we can say that, okay, this is the function, available function for the region 1. Then let's go to the region 2. In this case, we have cx plus d, and also we can apply the boundary condition phi x equal to L, and this is now corresponding to still 0. So why do we have such kind of boundary condition? Because we have assumed that this is the boundary condition for our green function. And now it is corresponding to C times L plus D. Okay, so D, simply speaking, now D equal to minus CL. Then when we just insert this expression, then now we can say that C parenthesis X minus L, end of parenthesis. Okay, that will be the form of our solution here. Okay, do you have any question? So now think about this form. Now let's just delete in the intermediate steps. So we will just have this form, and we will have just this form. Yes. So now we have two different values corresponding to A and C. However, also we can say that phi is a continuous function. So when we insert x equal to x naught, they should have the same value. So let me just apply this expression. So when x equal to x naught, the function value should be a times x naught. And also when we insert x naught, then it should be c times x naught minus L. And both of them should have the same value in order to guarantee the continuity. Then what happens? So ax naught equal to cx naught minus cl. So our goal is to express any of them with other quantity. So simply speaking, for example, c can be expressed as x naught minus l in its lower part, and here we have x naught times a. So are you all with me? So simply speaking, when we just insert this c into here, then let me just delete it. Then I would say, since c is given as x naught minus l, x l a. Yes, this is the equation for part 2 or revision 2. Now you know that we have only one single unknown variable or unknown coefficient a. So once we set this a, then everything will be quite easy. So everything will be determined. So we have the complete solution. So let's say that this is a. Yes. Then we have this expression, because we have assumed the continuity, and that will be the solution for our green function. Okay, do you have any question up to now? So I just introduce this solution procedure. Since the green function has highly localized, uh, source term, so except the point of that highly localized source term, we can easily solve just a homogeneous equation without any source term. Then after dividing the system into two pieces in this one-dimensional approach, then we can solve each inside each region and try to apply the continuity of the solution. Then now we will have this form. Okay, so please let me know if you have any question. Okay. Then now let's go to the final step. to finally get the value of a. So, how can he set the value of a? Some guy says that okay, we have done already many things, so just to leave it there. We don't have to know about the unknown coefficient a. But you know that this is not the case, since we have not used the information about our source term. Up to now, we have not used it. The only information we have to use is we just made yes, so at x equal to x naught, there is something strange that was used. Exact magnitude of the source term has not used at all. So now we will use this form. Okay, how can I use this form? Once you have the Dirac delta function, then one way to make it simple is just to integrate it. Then you will find really good progress. So let's say we wanted to introduce a certain integration from minus infinity to positive infinity, or for example, yes. However, the domain is restricted to 0 to L. For example, let's say that we wanted to start from L 0 and end at L when we make the integration. So when we make such kind of integration of our Poisson equation in the lower side, then what will happen to our Dirac delta form? Yes, delta x minus x naught. So from the definition of our Dirac delta function, then we will have the unit value as a result. Okay, that's good. However, so instead of that, how about this? Instead of that, I just integrate this Dirac delta function minus a certain epsilon. So this is not permittivity at all. This is infinitesimally small quantity, and also this is infinitesimally small quantity. Then what will happen to our Dirac delta function? So epsilon is quite small, however it is slightly larger than 0. Then what will happen to our integration? So could you please answer my question? Okay, so my question is just to answer or just to evaluate this integration. That was my question. So what is the result of this integration? Okay, Mr. Park, thank you, but I need a certain concrete form which can be expressed as just a number or a certain symbol. So could you please refine your answer? Mm-hmm. Okay, so how about your opinion, other students, Mr. Park and Mr. Jung? Okay, 1, 2 epsilon. And how about Mr. Park? Okay, okay, so the answer is also 1. So I think that Mr. Han is a little bit uh, confused about this Dirac delta function. So of course your answer to epsilon is obtained by this form. Yes. So if we take this integration, then obviously we will have 2 times epsilon. However, the integrand in this integration is not just number 1, but it is Dirac delta function. So Dirac delta function is, it's from its definition. So this number should give us 1. Okay, good. Then now let's go to this part. Now we have this condition. Then let's try to integrate our Poisson equation for this short distance. Then what will happen to our left hand side term and right hand side term? Then the left hand side term will be integration of our second order derivative. Then you know that this will give us simply the difference of our first derivative evaluated at x naught plus epsilon and x naught minus epsilon. And also the right hand side give us just number 1. So now you know that this is the integrated form of our Poisson equation nearby x sub naught. So that is quite obvious, and now we can evaluate these two derivatives. So how can we obtain these derivatives? For example, here we have two derivatives here and there. And this one, the first one, is corresponding to the region 2 function. And this guy evaluated at x naught minus epsilon, that is corresponding to region 1 function. So simply speaking, when we take the first order derivative of region 2 solution and region 1 solution, we have to have their difference as 1. So this is region 2 once again, and this is region 1, and when we take the derivative we will have this form. How can I have this first derivative in the region 1? Obviously we will have just a. And how about this? So in the region 2 expression, so we will have just x naught minus L and A. Obviously this x naught minus L term in the nominator becomes negative because x naught is smaller than L, and this is a negative number and this is a positive number, so we have a negative slope here. So let me just write down here in region 2 our first derivative becomes x naught minus L times a, and our region 1 derivative is given by just a. So when we just collect them all, then we will have x naught minus L, x naught minus x naught plus L a. So I think that you can easily understand this one. So they are deleted or cancelled out, and it should be 1. So from the all of our calculation, now we can find that a is simply given by L x naught minus L. Okay? So are you all with me? Okay, then good. Thank you. And let's just finally write down the solution. So since a is given by this number, so we can write down here explicitly x naught minus L times x. That is the function, the solution phi in region 1. And when we go to the region 2, things becomes a little bit more complicated, but let's just evaluate it. So x naught minus L and x minus L, and eventually x naught minus L. Although it looks quite complicated, but you can easily understand. They are cancelled out. So our solution now becomes L here, x naught here, x minus L. That is the value of our phi. Of course, here now our question is, what is the value at what is the value of our function at here? And the answer is quite obvious. Now we can say that when we insert x naught into it, so it becomes just L times x naught minus L. So this is the function value at this point. Of course, I wanted to say that since x naught is larger than 0 and smaller than L, so when we evaluate this function value, it becomes negative. You know, this is a positive number, and this guy becomes a negative number. Overall, it has a negative number. So let me just finally draw it in a right right sign of this midpoint. So solution of this simple equation is given as this form. Here you will have a certain form here, and in between they will have yes and Yes, that will be the solution. And once again, this function value is given by x naught minus L and L. So simply speaking, so once again, it's slope here given by x naught minus L, because here we have x naught difference, and within this x naught difference the function value changed by amount of minus x naught x, oh sorry about so is there anything wrong in my explanation? Mhm. Okay, so now this is the slope, and now when you go to the second region, then now we have the difference here given by L minus x naught, and difference is the same, so now it becomes the slope now becomes naught minus x naught L. That will be no. I don't think that this is the right one. Okay. Um, sorry about that. So let's just say this function value is given by L times x naught x naught. So the difference between this and that is given by minus of this number, and that is divided by L minus x naught. So they are cancelled out, so we will have just positive. So sorry about my confusion. So anyway, from this solution we can evaluate the slope in region 1 and region 2, and simply speaking, when we take the difference between this region 2 slope and region 1 slope, so region 2 slope is given by x naught over L and minus x naught over L minus 1, that becomes really number 1. Good. So it simply means that this one, this function really satisfies the Poisson equation integrated over small range around x naught. That is quite good. And now you can see that this one. For example, let's now compare these two cases. Let's consider two cases like this. You have introduced your Dirac delta source at the midpoint, so happen to be your x not equal to just half of L. This is one case. Then what will be your phi at x naught? Obviously it will become just so here we have L and half of L multiplied by minus half of L, so we will have so we will have just minus a quarter L. So for example, that will be in this case that will be the form. Okay, they are symmetric. But now think about another case. Instead of this highly symmetric point, for example, let me just introduce x naught equal to just tens of L. Then let me just evaluate the function at the point x naught. Then in this case, the value will be L times a tenth of L times minus, yes, we will have this form, and still we have a negative sign and L. However, the answer would be 0.09. So this is corresponding to, yes, this is corresponding to minus 0.25 L. However, in this case, if we insert it here, then its value is much smaller than that. So yes, so now you can understand, or depending on the position of your source, although you have introduced the same amount of source, so source amount is just given by Dirac delta function. So when integrated, it becomes just 1. But instead of that, you just say that this is given by depending on the position of your injection, or the depending on the position of your source term, the response becomes quite much different. Okay, so up to now I just introduced how can we solve the Poisson equation with the Dirac delta function in a simple analytic way. So do you have any question on this explanation? Okay. Good. Then now let's move to the analogy to the discretized system. Now you know the analytic solution. Then of course that was possible because the equation was so simple. However, if we go beyond the Laplace equation and its corresponding Poisson equation, we will have much more difficult equations. So we have to develop the scheme. We can solve those equations numerically, not analytically. So let's just do it together with me. So, however, the solution procedure is amazingly simple because this is nothing but just Poisson equation. So in order to discretize the Poisson equation, you have studied all of necessary skills. For example, at a certain x sub I, so you can integrate your system from, or your equation slightly smaller than half distance before x sub I and half distance after the x sub I. So please do it together with me. Then you can immediately understand that becomes, yes, so evaluate that xi plus half minus, you have done it already in your previous homework. Yes, now you can have the left hand side. Left hand side is quite easy, but point is now this one, Dirac delta function. So when your integration range starting from x sub I minus half delta and ending at x sub I plus half delta, if your integration domain contains x naught, then you will have just a positive number 1. And if that is not the case, so your integration range does not contain this x naught position, then of course you will have just number 0. So instead of this Dirac delta, now you have the Kronecker delta. Okay, so simply speaking, now you have something like this, xi and x naught. Of course, you have to understand the difference between Dirac delta and Kronecker delta. Kronecker delta simply means that your two arguments are the same, then it simply becomes 1. And if they are different, then it becomes just 0. However, in the case of Dirac delta, the Dirac delta is not defined in such a way. Only when integrated over certain range containing the x naught position, or the argument becomes 0 position condition, then it will give us number 1. So simply speaking, here we have Kronecker delta. Okay, so then how about the boundary condition? So boundary condition, we have just to use phi 1 equal to phi n equal to 0. So simply speaking, when we have a look at our matrix, there is no change from our usual Laplace equation. Everything is exactly, that without any single modification, this is the same. And how about the solution? Yes, this is the solution vector. And now we will have this form. Please have a look at it. So we will have 0 for the first node. It is because we have applied the homogeneous solution for or vanishing solution for node 1, and of course we have again 0 for the last point. You know it quite well. And even for other points we have 0 and 0, but this is not related with the boundary condition. This is related with our Kronecker delta. However, for learning this way, eventually we will have a certain position where we have number 1. Why do we have number 1? Because at that discretized point we have introduced Dirac delta form, and here we have a certain form this way. So are you with me? All of you, please confirm that you have understood this discretized form. Without any modification, you will get the system, the matrix system for your green function phi, here written as phi. Obviously, we will later introduce a different notation, but for a while, just to treat phi as a solution variable. Okay, so now I think that's it for today's lecture. So now you can understand, although the new solution, new equation looks quite complicated. However, when we make a discretized system corresponding to our new equation, then it's simply represented as what? As a modified residue vector without changing the, I can say, the system matrix itself. Are you with me? So simply speaking, now assume a case where your normal Laplace equation solver. So in that case, previously you had such a matrix equation, and you have a certain matrix both containing the discretized second order derivative operator, at the same time the boundary, directly boundary condition for first node and the last node, and at the time the solution, or the right hand side term, residue term, is given by in this way, and finally 1, or sometimes, or depending on your case, becomes 1 0 0 0. Important thing is whether the exact value of 1 or 2, 3, that doesn't make any sense. So important thing is whether this is 0 or not, or this one is 0 or not. That is important. We can always introduce normalization. So point is which one is non-zero. In this case, actually your phi can be regarded as what? So let's call it this matrix as A, and your phi can be considered as this way. Now your phi can be inverse of your your phi can be regarded as inverse of your A multiplied by certain form. However, the form contains all zero component and only non-zero at a certain position 1, or all zero and only non-zero at a certain position. That was the solution of your Laplace equation solver. Then now move to our green function. In this case, it is obvious that still we have exactly same system matrix A. So if we write down the solution phi, it is still given by inverse of A multiplied, here we have certain vector. However, there is also one non-zero value, and non-zero value is assigned in a certain position. So the position of this non-zero value really depends on your x naught. Your x naught determines where it should be located. But anyway, point is, in the case of Laplace equation, your non-zero position was the first and final, the boundary one. And in the case of this green function, now this non-zero value occurs in bulk node, not the boundary node. Okay, so now you can understand that the situation is both of your phi from Laplace equation and phi for your green function, or the Poisson equation with the Dirac delta source, can be regarded as just taking certain information of your A function. So actually inverse of A. You have certain inverse A function. Oh, it is the matrix and it has contained full information about your system, and this multiplying certain vector or certain vector simply just to pick up certain information, partial information out of it. For example, in the case of a Laplace equation, you just take the response of your solution with respect to the surface or boundary excitation. So, although your system can react to both of terminal excitation or bulk excitation, but now your Laplace equation just takes the response of your solution variable with respect to the terminal excitation. And when you go to the green function case, now instead of this bulk terminal excitation, now it says that we are now observing the response of our system with respect to the bulk excitation. So by collecting them all, what will happen? So now I'm asking this question. We have inverse A, and for example, we can have 0. Oh, sorry. Let me just start from this obvious one. Starting from 1 and all 0. Yes, this information can be obtained from what? Can be obtained from this Laplace equation. And 0, 1 and all 0. How about this? This can be obtained from what? Obtained from your green function. And how about this? 0, 0, 1 and all 0. That can be also obtained from our solution for this Poisson equation, and continue this procedure until what? So 0, 0, 0, 0, 0, 0, 0, 0, 0 and 1, 0. Up to here, these informations can be obtained from the green functions. Finally, yes, now we have 0, 0, all 0, and finally last element becomes 1. This is once again the solution of a Laplace equation. And you can individually calculate these functions repeatedly. Insert 1 here, insert 1 here, insert 1 there. Then you will get many different solutions. 5, 5, 5, 5. We get many of them. Then finally, why don't we just concatenate them? And this is a vector, 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 vector. So let's make certain square matrix. This is a collection of your green function or your solution of Laplace equation. And now you have A inverse, and multiplied by what? By your 1, all 0, 1, all 0, 1, all 0, blah blah blah, and 1, 0, and 1. You have multiplied this way. Then finally, you can easily understand this one. All diagonal components are unity and all other off-diagonal components are vanishing. This is just identity matrix. So simply speaking, the collection of your phi function just becomes inverse of your A matrix. So what is this? What is all kinds of this information, all kinds of this discussion? It simply means that green function and your Laplace equation is just taking the part of your inverse A function. All information is hidden in inverse A function. So what is it? So inverse of your system matrix determines the response of your system. So depending on your interest, sometimes you are interested with the terminal excitation, or sometimes you are interested with the response to bulk excitation at a certain position. But if we consider all of those cases, eventually we realize that the full information is certainly hidden in this inverse A function. So now you can understand the solution of Laplace equation and the solution of the Poisson equation with the Dirac delta function. They can be treated in a unified manner. So they are not much different. Although in an analytic sense they are different. Yes, they are different. However, when we make this matrix form, we can easily understand they are just showing certain aspects of inverse A matrix. Okay, so I think that is enough for today's lecture. So I just wanted to ask you have the homework number 19. Homework number 19 is simply calculate the green function. So assuming certain position for your Dirac delta function source, then just to calculate your green function as a function of a position. Of course, you can change your source position, then please calculate it. Okay, so do you have any question? So since time is up, if you have any question related with this green function, then please send me on direct message through our Slack system. Okay, thank you and see you Wednesday. Please implement your green function. So that is the simplest one, and we will learn it later in a more general circumstance. Okay, thank you. Bye.